question, I'm gonna solve this question for the, finding the deflection using the double integration. So what we have here, we have a triangular distributed load. We have from this side and the other side. But here he gave me a hint. What he said here, he said for convenience, select the origin of the axis, the midspan of the position of the elastic here. So he said here the midspan, choose x-axis is from this direction, so that means this point is going to be the origin. What that mean origin? That mean y here, y-axis, and x is a start from here. Okay, so in this case what we're gonna do is like this. Of course we know the first step is to find the reaction. Okay, so we need to find the reaction. We have reaction 1 r1 and we have reaction r2. How can we find the reactions? Of course we're gonna find the reaction by using by symmetry, by the symmetry r1 equal to the r2. Because they are symmetry, we have r1 and r2, they are equal. So how much? So you see each triangle has a force. How much this force? The resultant of the triangle is the height, which is w naught, times the width, l over 2, and divided by 2. Why? Because the area of the triangle, which gonna be w naught l over 4. So r1 equal to the r2 and equal to the fourth or quarter w naught l. Okay, so this one. The second thing is to find the reaction of the the moment equations. We need to find the moment equation because we need to say d square y and dx square equal to the moment x dx. We need to find a moment equation. Here y double dash is the same d square over dx square. How can we find the moment equation? We have f1. So here, so I'm cut here, like cut in this location, which is x-axis. Okay, so if I cut in this location, what we have? We have the first reaction 1. So r1, this is the moment. r1 times the distance. How much the distance from r1 to this section is l over 2 plus x. So l over 2 plus x. Okay, this is for r1. What we have also f1 and f2. Okay, for f1 is going to be minus f1 is the resultant of this triangle. Okay, which is equal how much? Equal to w naught l over 2 divided by 2. So I'm going to say which is w naught l on 4, this one. Okay, times the distance. How much the distance from f1, you see, from f1 to this section? How much this distance? So this distance equal to l over 3 plus x. Why l over 3? Because we know that the resultant is affected on the third, sorry, it should be, yes, this f1 from here to there is gonna be 2 only 3 of the distance. So the span is all over 2, so it's gonna be l over 3. Okay, so it's gonna be, as I said, 2 only 3 l over 2 plus what? Plus this distance, which is x, which is the same. It is third l plus x. We have also minus f2. What about f2? f2, we need to find it by using y. We have x, so I'm gonna put it here like that. So we have y, we have x. I need f2. Okay, so if we continue this, we have this one is w naught, and this distance is L over 2. I'm gonna find y in terms of w L over 2, which is here. I'm gonna say y on x should be w naught L over 2, so y equal to w naught x on L. So I'm saying minus f2, f2 in this case, so here f2 is gonna be y times x on 2, correct? Because it is area of this triangle, y, x on 2. How much y? Y we have it here. So I'm going to put here y, which is 2w naught L x times x on 2. Okay, which is this one. This one. So 2 with the 2. So w x square on L, which is the same, this term, times the distance. Which distance? So it's going to be the distance from this to there, which is how much? Is going to be third of x. Third of x. So this is the equation of the moment. So I'm going to arrange it. I'm arranging the equation. So we have this equation for the moment. Then we need to make integration. So the integration is, we're going to integration for the first and the second. So we have c1 and c1x, and then c2. To find c1 and c2, so here, what we have boundary condition. What is the boundary condition? The first boundary condition is, you see, because we have reaction R1 here, how much x here? Or we can use this one. I'm going to say at x equal to the L2, y equal to the 0. So for boundary condition, you see, at x equal half of L, y equal to the 0. So from this equation, I'm gonna find one condition. Here, for example, they said at x equal to the 0, y dash equal to the 0, which is the slope, you see. So because we have deflection like this, symmetric, so here the slope, which is dy on dx, or equal y dash equal to the 0, where at x equal to the 0. You can use this condition, or even you can use the second condition, which is at x equal half negative L over 2, y equal to the 0. So any condition you need to use. So I'm going to use the first one, at x equal to the 0, y dash equal to the 0. Then we can find c1 equal to the 0, because I'm going to use this equation. I'm going to say ei y dash is going to be 0 equal this 0 and this 0, then c1 should be equal to the 0. After that, we're gonna use another condition, which is x equal half L, y equal to the 0. So on this, we're gonna put it in this equation. So 0 is gonna be 1 for a w naught L square, and in terms of x, I'm gonna put x equal half of L, which is this one, half of L, this one. Then we can find c2. So c2 is negative 3 and 640 w naught L power 4. Because we have c1 and we have c2, then we can again put c1 and c2 in this equation. Okay, this equation. Again, we said c2 is 0. We have c1, which is this number, c1. Then the final equation for the deflection is this one. What he said find deflection at midspan. How much x equal, if you can see here, you assume that the x starts from the midspan, correct? So this is x. So at midspan, x equal to how much? Equal to the 0. So I'm going to say at x equal to the 0, which is midspan, ei y max equal to, So this is gonna be 0. Sorry, this is gonna be 0. We have this term, only this term, which is um, negative, and at x equal to the 0. Yeah, yeah, we have this term, and then after that we can we can just this here for, you know, to sample the equation. So the answer is going to be this one, which is deflection. Thank you.